Hello, everyone. Merry Friday. Today we're going to be building ZIO from scratch. Let me share my screen, particularly IntelliJ, and make sure that my notifications don't bother us. Cool. So yeah, new project, pretty empty. There is an empty ZIO trait here. There is this little file that I've crunched over to the side that we are going to use to motivate some examples and to force us to implement some methods. But first, let's just talk about what we're going to do. And it's in the description, but give a little more detail, which is, we're going to rebuild ZIO from scratch, a slightly anemic version of ZIO to begin with. Basically, if you just jump into the ZIO code base, you will see that while being, I think, quite well written and clear and nicely documented, there's a lot going on. And there are many files, there's many features, many optimizations to make it fast and performant for adding, nice little edge case handling and special features that people have requested over the years. Code bases get complicated, but at their core, the core idea of ZIO is actually quite simple. It is designed in a way that is useful to designing lots of libraries in a functional manner, something that John refers to as a declarative encoding. So it's this functional domain that helps us work with concurrent and asynchronous effects. We can have error modeling and error handling and concurrency, and we have the ability to provide environments. These are all amazing features, but we're going to start with a simplified version. ZIO, you may be aware, has normally 3 type parameters, an R, an E, and an A. And as you can see from here, I've limited us to just the A. To start with, we will over time layer in those other features, but for now, we're going to start just with a single type parameter and also with a much simplified implementation, which will slowly add real world complexity to in order to sort of be motivated by the need to solve real problems, which is why, ZIO is more complicated than what we're going to start with. It's because the actual encoding that you'll see in the ZIO code base allows us to have, stack safety and much better performance and error handling, etc. However, in adding that complexity, the beautiful, simple, clear skeleton of how these libraries function might become slightly obfuscated. So we're going to start from scratch. We're going to keep it really simple, yet build it in a way that we can sort of make minor changes as we go along to add these other features. And so hopefully you can sort of trace the evolution, and as things get more complicated, we'll all still be able to follow and still see inside of the complication, the core ideas that undergird that complication. I hope that makes sense. It should be really fun. We're not going to get through all of it today, but we sort of do have a plan for getting somewhere satisfactory today, and hopefully something surprisingly complicated for the lines of code that it requires to write it. And then we're going to add more cool features over time. And we can also use it as sort of an opportunity to go on some minor tangents, follow some minor tangents to talk about just, tricks that we use in Scala, functional programming tricks in Scala in general, or just some syntactic niceties or features of the Scala language that help us make the API shinier and nicer and better. So yeah, it should be a good excuse to talk about a lot of fun things. So with that out of the way, I will take a sip of LaCroix. Official sponsor of Symposium. And
I wish we would do a lot better if we had sponsors.
Yeah, it would be great. Yeah, right. Not actually.
If anyone wants to offer, we're open to proposals.
As long as it's LaCroix, I don't want to drink Spindrift, that wretched other alternative. No, I'm just kidding. Okay. So let us begin. Here I've just mocked out an empty trait, and we're going to motivate adding features and functionality and code to this trait by a series of examples that I have over here on the right-hand side. So we have a series of little empty case objects, or just objects, and we're going to slowly add features to them, add features to ZIO such that our version of ZIO, such that these can compile and then execute to our liking in that order. So let us begin. First things first, we want to be able to put things into ZIO, whatever that means. Just this is often something that'll show up in different functional domains, whether or not you have a parser or a JSON encoder or really anything else. If you have something that's parameterized by a type A list, an option, you might have a value and want to lift it into that context. So you want an int, you want to put it inside of an option so that it can work in other option code, maybe inside of an option for comprehension or a list for comprehension or something. So there's often a way to just take a pure value that you have your hands on already and put it in whatever contextual box you're dealing with. In this case, is ZIO. So what we're going to do is implement and get this function to compile. This function that's going to be called succeed now. It's going to take some type, in this case, a person named Peter, and put Peter inside of a ZIO. And so we want to get back a ZIO of person. And then running that ZIO effect, this description of a Peter, whatever that means, is going to hopefully print out the context there. So this is going to force us to get a little bit of infrastructure out of the way. As you can see here, I've made this ZIO app trait, which doesn't really do much right now. So we're also going to have to think about how we want to get this to run. Okay, let us do this. So first things first, we need a companion object to store this method on. So I can just create an object called ZIO. Hopefully, because it wants to do it in this file. So my usual trick of just letting IntelliJ do it for me might not quite work, but maybe it will for now. Yeah, okay. So now I can have it create a method called succeed now. Lovely. And I'm going to sort of mush this over to the side and maximize screen space as much as I can, whilst also being able to see both sides. Okay, so IntelliJ was very sweet, but not too smart here in that it hard-coded it to giving us exactly a person. But we want succeed now to work with any type. So we're going to give it a type parameter of A, and then accept any value of A, and then get back a ZIO of that A. So this is the process of taking any pure value of any type and getting us back a ZIO with that type stored inside of it. Okay, so how are we going to implement this? We don't even really know what we want ZIO to do right now. So we're sort of at this first stage going to have a bunch of these different constraints kind of informing each other as we figure out what we want things to even do. We know we want to be able to put values in a ZIO, but how can we confirm that? What does it mean to put a value inside of a ZIO? Well, we can prove that we put the value inside of it by somehow running the ZIO eventually. So we might want on our ZIO trait to have a method called run. That could work potentially. That could get us back our A. Maybe that's how we could start. And this would actually be quite trivial to implement. I can just make a new ZIO of A, and the run method could simply just return the value. So that would work. And it's not beautiful, but let's see. Okay, so let me do this. Okay, so we have now a ZIO here, and in the main function, I can now simply print, the result was, and then I can call run, and we'll see what happens. And let me just comment out everything else because it is now going to want me to write override because I've given no implementation for run. Okay, so let me try to run this and see what happens. We're probably just going to see the result was Peter, hopefully. Yes. And there's a lot of noise up there, but here it says the result was person Peter. So yes, we can put a value inside of a ZIO and get it back. It's not terribly exciting. It's all very trivial seeming and silly, but this is going to grow over time. This is the sort of the bare minimum. However, we also have to think ahead a little bit. While this does work in this case, we do have to sort of encode in the basic sort of fundamental operators on our trait here enough. We need to give enough headroom to satisfy not just these simplest of constructors, but as well more complicated constructors that we know are coming down the line. And while we could wait until we get there and let that force us to rewrite things, that might force us to write a whole bunch of code. So we're just going to think ahead and realize that ZIOs, we know already that ZIOs are going to have to deal with asynchronous code. And so this is going to be potentially a description of some asynchronous operation that might take 10 seconds to return us a value of A. It's going to be hitting a very slow internet connection somewhere in the other side of the world and get us back a person from, suck a person out of Australia for us. That would be bad, because this would imply that this is not asynchronous, right? So that would mean that this is either going to have to block, or it's going to lie, or and blow up. One of those two. It's either going to block or blow up, really, if it's actually going to really represent something asynchronous, and we don't want it to be blocking. So we have to actually have a different type signature here. And so instead, what we could do is have run take a callback, sort of this old school, callback style code. So here's the callback, which will accept a function from 80 units and just simply return unit. So instead of doing things like this, we're instead going to have a method called run, which will accept a callback that takes an A. So basically the way this is going to work is the user is going to give us the function, what is sometimes called the continuation, which is just another fancy word for callback, or just another fancy word for a method of some type A to unit, where A is the result. So we've kind of inverted the control of this function, where this run function is going to be able to call this callback, and then that callback will take it over from there with the result. So this might decide to call the callback in 10 minutes, in 20 minutes, in 3 hours. When it's finally gotten the result of that person, then it can call the callback. So this will now work with asynchronous code. And that's kind of the more complicated version of run that we'll need to satisfy asynchronous code. However, we can still get it to work with simple versions, synchronous functions, like for instance, running something that we already have, where we already have the value. So in order to do this, we can just simply call callback with our value, and that will compile here. And then down here, we need to change things a little bit. So instead of calling run.run there, we're instead going to say run.run. And then here, we're going to get back our result. And we can put that result in here. So hopefully, with a little bit of reshuffling, this will still work. Yes, okay. The result was person Peter 88. Now, as we actually get into asynchrony a little later, we're going to have to change this a bit, because Java will probably quit if this actually takes 10 minutes, because it's going to complete immediately. It's not going to wait for the result of this callback. So we're going to have to make sure that it actually waits. If we wanted to, we could just add like a thread sleep here, but that would be annoying. So we'll take a look at a simple way to get some blocking in this function where we actually want to see our results. But for now, this should be fine. But just let's keep that in mind if things start to break later on and we don't get results printed when we expect them. Okay, so spending a lot of time on the succeed now. There's one last refactoring I want to make to this before we can build on top of this. And that is, instead of just making this be a trait like this, where we're making a new ZIO, and then therefore each of these sort of operators, these fundamental operators, will just be instantiating a new trait that defines its own run method. Instead of that, we're going to make it a little more powerful and make this a sealed trait. And instead of doing this, we're basically going to keep this implementation. I'll cut it for now, but instead we're going to implement each of these basic operators and some of the combinators as case classes, members of this sealed trait, subtypes of this sealed trait. So this is going to be ZIO.succeed. This is called ZIO.succeed. And this will take the value. And we can now create a case class called succeed, which is going to have a value of A, and it's going to extend a ZIO of A, which means we basically just throw the same method that we had in here. So it's nearly identical, except now we have this nice named case class, which is kind of nice for two reasons. One, it lets the methods kind of become very trivial to write, because all we have to do, all we're really doing now is writing a sort of a node of a syntax tree, a very specialized syntax tree that is the syntax tree for a ZIO effect. So when we call succeed now, that takes the value. We instead translate it to sort of this description of calling succeed, just a case class, this data form of the method, which while we're implementing the actual we're outfitting this description with how to interpret that description, it is still, at least at this level, just a nice description value. And that's going to, especially I think probably in the next session, allow us to do some more clever things and make this thing stack safe in a much nicer way. But it's also kind of like satisfying, and it's nice and neat, because we'll be able to read out all of our methods without sort of their long implementations getting in the way in some cases. Okay, so there's ZIO succeed, and now it should all work just the same, because we've just turned a trait into a sealed trait. So now we can introspect it, match on it if we wanted to, these basic primitive ZIO types. So yes, the result was person Peter. Lovely. Cool. So now let's continue on a little bit to this one, this problem. Succeed now, as I've called it. And I just need to close that there. Okay. So here we're calling succeed now, and inside of succeed now, we're calling print line howdy. So let's see what happens if we run this object. Okay, we got howdy, and then we got the result was unit, which does make sense because calling a print line returns unit. So we're seeing the result being unit, and we're seeing print line running. So all seems right until I actually change this to be succeed now of the number 1. And I run this. What we're going to see is the result was 1, but also it's still printed out howdy, which is actually not the semantics that we want for ZIO. ZIO, these functional effects are supposed to be pure descriptions. So blueprints, they're often referred to as, of some kind of computation. So we don't actually want this to run its side effects. We don't want to execute this blueprint, take this recipe and bring it into the kitchen like until we actually try to run it. And because we did not specify howdy in here, it should not be run, but it is being run because if shouldn't be surprising, right? The definition of succeed now is going to take the result and put that result inside of the succeed node. And the result is that of calling print line eagerly. So right now, just by defining this at all, it's going to run this. Now we could change this by making this a def, and that would have that would also fix it because this line isn't going to get evaluated at all. But with ZIOs, we actually want to be able to keep them as vals. It's actually makes it way easier to refactor. That's actually a problem if you use futures. There's a huge difference between defining some future as either a def or a val. They have very different semantics, which makes it very tricky to refactor them because you could easily switch one to the other somehow, and then your program changes significantly. Things start running much more frequently or less frequently than you would have otherwise expected. So in the ZIO world, we want everything to just be a pure blueprint and not run. So ZIO, actually, the real ZIO does have a succeed now operator, but it is protected and it is, or private to ZIO rather. So we can use it internally in careful places where we know that it's safe to eagerly evaluate things for performance reasons, but we only expose to the outside world a different method called just succeed. So let me go down here and uncomment this thing. So ZIO succeed should not eagerly evaluate its arguments. So we can think about how we might need to make that happen. So let's make a method called succeed, which is going to be sort of similar. It's going to take an A. And the problem sort of is with the type signature. If you think about it, right? There's no way, if we're getting this value here, to prevent it from evaluating. So one thing you might think is like, okay, how would we prevent this from evaluating? Well, that's where the power of functions come in. We can accept a function here, which will have us change the syntax slightly. But if we do have a function here, this means that print line is not going to get evaluated in line when this is being evaluated, right? We have to call a function to actually evaluate it. So let's just start from here. And instead of this, let's do ZIO dot, let's call it dot effect. And for now, and we will just pass in this function to effect. So very similar to what we did with succeed, except this is going to take a function that's going to return an A. So I will add the type parameter, and let me, sorry, maximize the screen. Apologize for the shifting font sizes here. Extends ZIO of A, and then we can kind of steal this implementation, except let's think through it. Callback, we need to call callback with an A. How do we get an A? Well, we have a function that simply calling it will get us an A. So there we go. This should theoretically work. So let's see what happens. If I run this, we should obviously see how does ZIO get printed, and it was. But also, if we do not evaluate it, and we instead call, succeed now of 12 or something, just do any other effect in here, then howdy ZIO should not fire. So the result was 12. We do not see howdy anymore. So that shouldn't also be surprising either. We have trapped the computation in a function. It is not going to be evaluated until we purposely evaluate this, not eagerly, lazily evaluated. However, that's nice and all, but if you use ZIO, you'll know that you don't have to use the syntax. And in fact, it's a little annoying to have to use the syntax, right? Because this is kind of always just going to be noise here. We only care about this for the purpose of lazily evaluating this. So wouldn't it be nice if we could somehow, delete that part, right? Just delete, that would be cool if that were valid syntax. And it actually is. You'll see the problem is down here. This is, you probably know this, maybe that wasn't a magic trick for anyone, but this syntax, which looks just like a nullary function, a function of 0 arguments to an A, except missing its little unit there, is syntax. And on this side, you're actually able to just write normal Scala code. So you can delete the parens from there. You don't keep this. But I think it's kind of a funny little syntactic pun that they did here, where just by deleting that unit up front, you can sort of delete the corresponding parts from the call site. But it will maintain the semantics of a function. There's basically behind the scenes going to be a function here. And there's some magic stuff that the compiler is doing, because when you call value, you're actually getting the A back. But really what it's doing behind the scenes is calling this function, basically, except without that syntax. So that means maybe we're going to oh, wouldn't it be nice? Maybe we should keep percolating that down here. Unfortunately, this does not work in case classes. So at this point, we still do need to sort of wrap this secret function up inside of a real nullary function like this. But by using this syntax, we can get the same capabilities of lazy evaluation, except we don't have to have the ugliness. And now it works just the same as it did before. So that's kind of cool. That's called call by name, a call by name parameter, call by name. So it's just like, you're calling a function. How do you call a function? Well, you call it by calling it with parentheses. How do you call a call by name function? You call it just by referring to its name. So I think that's probably why it's called call by name. Yeah, not as complicated as it may seem, but that's kind of what I mean. Like if you were not familiar with the call by name parameter and you try to look at the ZIO library, you might easily become overwhelmed and confused, right? Because there are these multiple little syntactic tricks that the complicated libraries are using to give you a nicer API. And those tricks are kind of simple by themselves, but when in aggregate, especially as there's more complication and more indirection, it can become a little overwhelming. But that's kind of the basics of it. We want to wrap functionality up inside of functions like this and not just return the value for twofold reasons. One is so that you don't eagerly evaluate when you set it to a value like this. But also, sometimes the thing that you do in here that's getting you the value of A could explode. And if it explodes here, just when it's calling it here, before ZIO gets its hands on it, then there's nothing really much that ZIO can do to save you from that. You can't catch it. It's just your code's going to explode when this line evaluates, when this line is compiled, it evaluates, I guess, when your program runs and loads everything. But in generally, we want to actually catch that inside of the ZIO world and allow you to save yourself from those issues. Now, we're not into error handling yet, because that's going to add more complication and more type parameters, but that is another reason for having lazy by default for most constructors in the language. And in fact, in ZIO2, Adam made a very extensive PR making most functions be call by name, which should just generally, it has the effect of making things just work as you'd expect and just be safer overall.
Yeah, I think with the exception of high performance concurrent data structures, everything in ZIO2 is by name. And it's kind of interesting. I was thinking about this morning, and it basically eliminates a class of bugs. And there are other class of bugs, but that particular class of bugs basically eliminates, where in ZIO1 or even in other effect systems, you'd sometimes have a case where someone would accidentally embed a side effect into their ZIO and it would get evaluated at the wrong place. So you'd either get evaluated too early, or maybe you try to retry it and it wouldn't actually do anything. And this is something I've seen, it's not just a theoretical thing. I've seen it big organizations in production code, causing production issues in ways that are sometimes hard to track down, of oh, you're trying to update something, but instead of doing a new thing, you're updating an existing thing. And it's like making your Kafka crash. So it's actually like a pretty nice like quality of life thing for just making your code safer. And it's like such a like minimal cost. People who kind of say like, oh, don't do this, like have that kind of succeed now. It's like very slightly faster to do like that versus the succeed. But in the context of everything else we're doing with something like ZIO, it doesn't matter, and it just takes away that class of bugs.
Mm-hmm. Yeah, and hopefully now you can use that trick in your own library. So the only real detail is to know that you can't use it for case classes. So the trick is to make a method constructor that can have the call by name parameter, and then just basically lift it up into there. Cool. Nice. All right, so let's take a look at this. Oh yeah, this is just kind of silly. I even forgot why I did this one, but yes, now we have the ability to create sort of methods that return ZIO effects as well, a side effecting method. So we can create our own version of the print line function from the standard library. So now we have a ZIO-ified print line that simply takes a message and returns ZIO.succeed of print line message. But it's obviously only going to run it whenever we call this and not otherwise. Because it's lazy down here, which is great. Okay. So let's keep going. We now want to be able to do something a little more complicated. Now we can put individual values and side effects inside of ZIOs. But how do we build up more complicated effects? How do we build up applications? Well, we need some way of taking two effects and combining them together somehow. And in order to do that, one nice key fundamental combinator is the zip combinator, which lets us take a ZIO of some type A and a ZIO of some type B, and then get back a tuple of the A and the B zipped up inside of the ZIO effect. So not a tuple of ZIOs, but a ZIO of a tuple. And that's what zip should do for us. So let's see if we can implement zip. Great. Thank you, IntelliJ. So we're now going to accept a ZIO of a B, not of a byte, autocomplete. Great. Which means we have to annotate this with a B. And we're going to get back a ZIO of a tuple of A and B. So that's what zip does. It's on a lot of different types, including ZIO. Very useful one. Okay. So how are we going to implement this? Using the same technique that we did previously, which is going to be making another case class. Nice. Okay, so we're just going to have this accept all of the arguments, everything that it needs to actually implement its run methods. So if this were a node in a syntax tree describing ZIOs, then well, in order for zip to hold all the information, it needs both sort of the left-hand side and the right-hand side of the zipping. And then we can create a new case class called zip. We're going to parameterize it by both A and B, and we can call these left of A and right of B. And this will return for us a ZIO, extends a ZIO of a tuple of A and B. Now we can have the method get stubbed out for us. So now this is getting slightly more frightening looking, but we're going to have to, this is going to be less trivial in these implementations, but it still shouldn't be so bad. We'll think through it together based on what we need. So yeah, there's when writing these sorts of polymorphic functions with a lot of type parameters, it can be scary, but it can also actually be quite freeing because there are only so many things that actually even make sense. I like to start sort of from the end, or maybe both ends, burn the candle from both ends. It's a nice tactic to use, which is to say, okay, what do I eventually need to return? And well, a unit. We eventually do need to return a unit. So really, we could just return unit here and that would work. But obviously, in order to sort of audit ourselves, we can say, does this feel right? I think obviously no, but more specifically, why doesn't it feel right? It's because we left a whole bunch of stuff on the floor. We had all these parameters, we had all these arguments that we did not touch. So generally, you should probably use everything. If there's something like, if you're making a recipe and there's just like mysteriously, or like you're assembling some IKEA furniture and there's mysteriously like a whole pile of nuts and bolts that are remaining, right? Something is probably going to break eventually because you were supposed to use those. They're not very generous with extra nuts and bolts. So yeah, how do we do this? Well, so while the return signature is technically unit, the actual value we really want to get is a tuple of A and B, right? In order to call our callback function, because we've turned this into this continuation-based style, this callback style. that's kind of our real return value, is the argument to our callback. So let's start there. And so we need to get back a tuple of A and B. So we need to get back an AB. So that's kind of like the step I like to do. So how are we going to get back a tuple of AB? Well, where are we going to get an A? Right? In order to make a tuple of A and B, we'll need an A and a B separately. So the only place we can get an A, possibly, if we see it in the type signature, is inside of the left-hand side, and the right-hand side has the B. So we're going to need to get those out of there. That's really the only way that we can call this. So the left-hand side is a ZIO. How do you get the value out? Well, you have this run method, which accepts a callback from A to unit. So in here, inside of this callback, we now have access to A. Likewise, if we want to get the B, we can call run on the B. And we have to do this in a nested fashion because once we're outside of this callback, we will no longer have the A. And we need both of them simultaneously. So there's some sort of sequentiality here. Now we could have right on the outside as well, but just due to the way I think we may expect things to work, we want the left side to be before the right side here. Okay, and now we have both an A and B, and we're able to call the callback with our tuple. So that works. Huzzah. Okay, and it's not horribly complicated. And these can end up looking horribly complicated in real world situations. However, if you follow those series of steps where you sort of just keep moving the line, moving the chains just slightly, figuring out what you need, and then figuring out what you needs, and where you can get it from, and sort of working inwards, generally you can implement it without thinking too much, and then just ignoring the frightening implementation that you've generated and just being happy that it works. Okay, so does it work? Let us see. We will now run this. Yes, indeed. The result was 8 and LO, whatever that means. So yes, that works. Cool. I think I see a Q&A. Let's see if there's a Q&A. Can you explain again why using case classes in implementation instance is a good practice? Thanks. Great question. Yes. Yeah. So, well, we're not quite seeing the full benefits of this yet. Currently, this is basically equivalent to what we did originally, where we just defined, we could have just been defining each of these in line. We could have just said a new ZIO of AB and just put the implementation here. Really, that would have been identical to this. However, what you do gain from this is the ability to, if we wanted to, we can make some sort of optimized method, which I don't think will really make sense yet. But then if I call match on this, we can see all of the branches of our ZIO effect. You would not be able to get that if you did not have a seal trait. And so theoretically, we can return a new ZIO of A that's optimized somehow. So we could see, if it's a ZIO effect of a, I don't really know. Actually, I don't think we can really do anything sensible here with what we have. But eventually, potentially, you could.
Well, even with this, we could say, how many steps does it have?
Sure. Yeah.
We may actually not be able to do that later. We'll see. We kind of give up some of that ability for other things. But right now, we actually could do that.
Yeah. So if we want to know the total number of steps that we're taking, it's 1 int, right? So succeed, I guess that counts as 1. Effect, that counts as 1. And then zip will be left.steps plus right.steps. Huzzah. So now we can introspect and do these sorts of interesting things. So let's see if we can actually get that to work. So here, theoretically, we should think that this is going to be 2 steps. So I can do ZIO.succeed now, I guess, and call .steps on this to get back a ZIO of an int. And
I guess we could debate whether zip is itself a step. It should be like left, right, +1 or not.
Constructor could not be, oh, and this is a silly thing because of, why is this sad? Oh, because it knows that it can't be that. This is that silly thing that occasionally happens. Let me convert this to a typed pattern, I believe. Here.left. Sometimes, oh, zip .left.steps, zip.right.steps. Please work. Yay, the result was 2. Okay, cool. And if we add another zip in here or something, we make this a lazy val and zip it with itself. Well, that'll actually recurse forever. So let's not do that, but zip.zio.succeed of 10 or 13. And running this now, we should have 3 steps. Don't need to make it lazy. So yeah, cool. So that's one of the capabilities you can gain from using a seal trait. Obviously, we're not really using it like this, but eventually we're going to, in the next session, Adam is going to switch this to being stack safe and using sort of a single loop function where it's going to be very important to be able to match on these different types and know what's what. So that introspectability is going to come in a great deal handy. So yeah, I hope that helps. And I also kind of just like it. I don't know. I kind of do it myself with data types. It's even though it's equivalent, because you might always want to optimize it later. And it's also, it just feels nice and neat to have these simple implementations. Okay. And why that didn't work, that, by the way, is unfortunately sometimes when using these complicated types in match statements, Scala 2 gets a little angry at you and doesn't believe you about the types here. So yeah, sometimes you'll find the need to switch over to the what is that called, the typed pattern rather than using the unapply pattern, which is a little annoying, but tis what it is sometimes. Okay, lovely, but we don't really need that method now anyway, so it's all good. Okay, let's keep going. Unless, are there any questions on the Discord, Adam?
No, we've been having a little bit of discussion on the side about the fact that with case classes, you can't do like a lazy val or have it be kind of by name itself. You've got to do like the smart constructor thing, and the fact that that's still true in Scala 3, even though Scala 3 makes a lot of other things better, it doesn't make that particular thing better. But
Gotcha.
yeah.
Gotcha. Fun debates. Fun debates. Yeah. Okay. Well, cool. So we have zip, which is important. We can take two subprograms and combine them together. But that zipping becomes immensely more powerful when it's also coupled with the map operator, which allows us to transform the contents of a ZIO. So if we have a ZIO of A and a function from A to B, we can get back a ZIO of B without actually running anything, which is very nice, very composable. And with zip, it's particularly nice because, so, well, here I did this one thing, but I can also make, say, perhaps a person ZIO, right? So now I have the ability to get back a ZIO of person by taking this zip ZIO. Let me basically copy this, but instead calling person and using the string as the name and the int as that. So you can take these individual pieces and combine them into more complicated data types and map over them. So yeah, let's implement this method, map. Okay, obviously, it was not quite correct here in its assumption of the types as usual, but nonetheless, it's good to have something there. So the actual type we need is a function from A to B, and it's going to get us back a ZIO of B. So on our ZIO of A, we can give it a function of A to B and get back a ZIO of B. Okay, great. So how are we going to do this? Well, it shouldn't be surprising by now. We simply call map, put ourselves in there, stuff all the necessary information in there such that in just a minute, down here, elsewhere in the code with A and B, with some sub ZIO, we can extend ZIO of B and then implement the actual method because we've propagated all the arguments we'll need from the call site down here into this implementation. Okay, and once again, guided by types, we can implement this. So we're going to need to call our callback with a B. How do we get a B? Well, from the function f. How do we get a B out of f? Well, we have to provide it with its argument A. How do we get an A? Well, we need to run the ZIO to get ourselves an A, with which we can call f on it to get a B, which we can then call the callback with the B. And hooray, it should work. Let's check it out. Boom. Okay, so I'm running this map ZIO now, which is going to multiply the string. Oops, what's, oh, steps. Yeah, that doesn't need to exist anymore. ZIO, zip ZIO. You can go back to zip ZIO. Cool, that's from the last one. So we're gonna run map ZIO, which is going to multiply our string LO by the number 8, and we'll get back LO. So the mystery has been revealed. That's the point of LO. It was laughing at you. Okay, so zip ZIO now can also return, hopefully, a person. Person ZIO. Yes, person ZIO is the mapped version of 8 in LO, and we should get back a person named Lo who is 8 years old. Amazing. So we can map over things. Quite trivial. Nothing is very complicated so far. Let's take a look at the next version, which will force some more implementations, some more methods here. So what if we wanted to take our little zip ZIO here and then print the result using the effectful, the ZIO-ified version of print line. So we're going to call the zip ZIO, map over it, getting the tuple back, and then print line ZIO. What are we going to get back? We're going to get back, the result was in effect if we look at the type of map ZIO, it's going to be nested, right? We have this doubly nested ZIO because map will go from A to B. This function goes from A, where the A is this tuple, and the B is the result of calling printline, which is another ZIO. So what we really want to do is be able to call run on this, except we don't want to run it eagerly in here in the map. That would be very bad and confusing and weird and not very composable. Instead, this is why we have the existence of Flatmap. Yay, Flatmap, which does not exist yet. But Flatmap, this is just like map, except it will flatten the nesting afterwards. Essentially, in the runtime, running that nested effect for us and passing its effect along, but we do not have to manually sort of call run, which would be horrible. So that's handled in a reasonable way by the implementation. So let's implement ourselves Flatmap, another incredibly common functional method here. So just like map, almost identical to map actually. So let me just copy all this, except it has the word flat in front. And also the return result is a ZIO. So it's nested. And we can call Flatmap, passing in once again the F and ourselves, and create the case class. And I'm actually going to also steal some of that information from up here because it's almost so identical, except this is a ZIO of B, of course. And then we can implement it down here. And even this is nearly identical, I think. Let's see, we need a B to call our callback with. How do we get a B? Well, then we have to run this ZIO. But how do we even get that ZIO? Well, we need to get an A. How do we get that A? Well, we need to run the first ZIO. So let's call the first ZIO, call run, get the A, call the F, which will get ourselves another ZIO, which we can call run with and getting the B back. And then finally, we can call the callback with the B. Huzzah. And I think I've added one too few or too many. There we go. Things there. Actually, if you peek extra hard, you'll see that the method signature for run on a ZIO of B is actually going to be this callback itself exactly. So we don't even need to necessarily create a redundant extra callback in the way. Like if you see what we did here, we just made a callback that simply takes the B and passes it to another callback. So this function is basically just has the same signature as this function, except it's a redundant sort of in between thing. So why even do that? We can just pass the callback right along. But it's good to figure those things out after you've gotten it to work sometimes. No need to be extra clever as things are still in flux. Okie dokie. Let us see if we see my beautiful tuple. I'm so proud of my beautiful tuple. There it is. So it's printed out. Amazing. Incredible. Okay. And now that we have implemented both map as well as Flatmap, we get for free a for comprehension. So we can now for comprehend our ZIOs. And here we go, my beautiful tuple again, 8 low, and then the result was nice. I couldn't agree more. Yeah, and that's just done by using for comprehensions now. Wow, beautiful, because if you desugar it, it is basically just flat maps and maps nested in a horrifying way. On and on and on. Cool. And at this point, we can do a lot of stuff. We can actually implement a good deal of functionality with just these basic combinators, and we can make some sort of higher level ones. If I do actually desugar this real quick, we'll see that we're calling map and then throwing away the arguments and then just returning this result here. That's such a common pattern that in ZIO we have a method called as, which allows you to just specify the type that you're changing it into. So we may as well define that. And at this point, we can actually value A, and I suppose we should make it a call by name parameter to be safe here. Oh, sorry, value B, rather. This is going to be some other type because it's just like a map, except we're not taking the beginning. And we can call self.map, throw it away, and then call value. So at this point, we're not going to implement ZIO.as, right? You could do that, but this is kind of a nice basic version on top of map that we can sort of build these higher level combinators in terms of the sort of the fundamental operators.
Yeah, I think that's the one maybe a little bit like watch out with like this pattern of like these case classes. And I think it's probably good overall, but I think it pushes you to think more compositionally about how you can implement things in terms of other things. Because there's like there's a cost of kind of a risk of like a combinatorial explosion of just kind of if everything becomes its own primitive. So you really like you got to think a little bit more about like what are the things that are actually primitives and what are the things that are can be just built on top of them. And I think that's probably actually a really good exercise to do overall in terms of API design, and results in code that's easier to maintain and refactor. But it probably does require, I think, a little bit more upfront thought, at least if you're kind of new to this style of design.
Yeah, that's a great point. It makes it more explicit in terms of what are these basic combinators, what are these core constructors of your DSL. Whereas if we were just making new ZIOs everywhere, it wouldn't really, there'd be no one place to look at all of the combinators. I mean, you have to sort of hunt around. When you make one of these, it feels very, okay, this is important, this is key, this is sort of fundamental. What is it? Yes, minimal and orthogonal. You want these core operators to be as small as possible, and also not step on each other's toes. So actually, to speak of that,
yeah, I was just thinking.
in terms of orthogonality, it's actually possible to implement map as well as zip in terms of Flatmap. We don't really need these to be core. I mean, they were simpler, it was good to start with them, but now that we have more complicated operators, we can actually sort of absorb these more basic ones.
Well, yeah, and I mean, another interesting thing here is like sometimes you get into a thought about like which is the most minimal set of an orthogonal set of combinators, because I think that's probably the most practical thing to do, and like that's what we like definitely do like in ZIO. You could actually do it another way, and you could say map and flatten are the like at least most orthogonal set of combinators, and then we could implement everything in terms of those.
That's a good point. That's a good point. Yeah, because Flatmap, even in the name, it's sort of these two operations, right? That are so you can break it apart across the scene, flatten map, and then implement everything else in terms of that. I think there's another sort of contributing motivation, which is that sometimes these primitives, like you might want redundant ones for the sake of performance. And I think why Flatmap is not a combination of both flat and map, even though technically it could be, and maybe that would be more lawful and pure, is that Flatmap is the most common operator in ZIO, right? Used in 4 comprehensions. It shows up everywhere. We want that to be have as little overhead as possible. We don't want to be constructing 2 instances of 2 different core constructors instead of just one. So sometimes for performance reasons, it might be worth making, if you did as a whole bunch, maybe hard coding that and do another fundamental one. But it's a trade-off, because then it might become more difficult to implement other optimizations on top of that, which might make it faster in the end. So yeah, good point. But in order to implement it as we have in ZIO, let's just stick with, let's just do Flatmap. Or yeah, just pick something. We don't have map or zip, right? In ZIO, it's just Flatmap. So I think let's do that. So how could we implement this? How can we implement map in terms of Flatmap? Well, by calling Flatmap, first of all. And then let's just write it out before we do anything clever. We need a function from A to a ZIO of B, but we only have an A to a B, so I can call F with A, and then we just have a B in here. So how do we get a ZIO of B? Well, we can call succeed now. This would be a great time to use succeed now. Even if it were private, I think internally we probably use succeed now. So that works. Also, if you want it to be super fancy, which I don't recommend, we could also do something like F and then ZIO.succeed now to make it super fancy. But as you see, it's almost the same number of lines of code and potentially could confuse more people. But because it's fancy and we're being fancy here, let's say fancy. I'll keep that's probably a smarter thing to do down below. And then for zip, well, we could just use a 4 comprehension. That's an easy way to think about it, right? We want to tuple up an A and B. How do we get the A? Well, we just call ourselves. How do we get the B? Well, we call that. And then that shouldn't be capitalized. And then, yeah, obviously, we could also desugar this and just have it be this. But yeah, may as well use the 4 comprehension for fun. Yeah, so now we can delete ourselves zip and map. Goodbye. And so now we only really have succeed, effect, and Flatmap. Cool. So good. Let's just check in. Good. We got some more time. Now we can get into something a little more juicy. So far we've just been sort of writing this. It's not very asynchronous. I guess theoretically we have the ability to. We have this callback driven implementation, so we could do it, but we haven't implemented any operators that really allow us to do anything asynchronously in the background. If we wanted to, we can sort of have some of these ZIO effects call thread.sleep inside of them, but that would kind of just screw with everyone and wouldn't speed anything up. In fact, it would slow everything down. But yeah, we can't run things in parallel. Can't do any of that stuff, which is definitely probably what you think about when you think of the power that a functional effect system gives you. It makes it really easy to write concurrent code. But we've done the first step, which is boxing up side effects and descriptions in blueprints, allowing you to compose those blueprints with some nice operators and having call by name parameters to make things nice and safe and make sure that everything is in the blueprint. Cool. So if there are no other questions, let's implement the first sort of most fundamental of the asynchronous operators, one, which in ZIO2 is called async. In ZIO1, I think it's called effect async, but we've simplified that, so it's just async now. And let's take a look at the signature for async. So I've given it a type parameter here. So this is going to be some ZIO that's going to return ourselves an int at the end of the day. And how does it work? Well, we call async, we get an argument here, which appears to be, obviously this is aspirational coding here, which I do recommend as well. I like, this is how I actually code. It's not just for these types of things, like feel the API in your hands a little bit. It feels better, right? Write the code you wish existed and then, hit option return or something to have it help create those methods if you'd like, which is a nice side effect. And I closed the window. So oops. Succeed. Let me put this back over there. Okie dokie. So what is this? So it's a function we're calling async. We're giving it a type. Then we get this, what apparently is something you can call. So probably a function that accepts the type that we ascribed up here. So we get a callback. And a nice way to think about this is actually we are handing off control to a third party. We're basically giving this block, this callback, this block, the ability, like a remote control with which to complete our ZIO effect. So, just that little black box with the red button that someone can press, and then it'll blow up the ZIO at their liking. Obviously, instead of a button you press, it's actually a function you call with the result. So you give this the result whenever you want, you drop the result into the box, and you'll see that result succeed or whatever. The ZIO will be succeeded with that result at that time. And if you think about it, if you look at sort of the core operation, the only unimplemented operation in our ZIO, it is this. It's the run function, right? Which is a callback. It's a function that takes an A. So that's basically what you get inside of this async block. You get the ability to implement really the core of what the ZIO is, which is a callback. You get to pass in this A. We're inverting control. We're spilling our guts of the ZIO to the outside world, which allows us to interact with non-ZIO libraries, such as something that's going to sleep for a second and then complete it, right? So you can use this to implement some silly simulations of long-running functions, or we could pass this complete function to a callback-based API, obviously, or integrate with futures or something else. So yeah, it's kind of a fundamental operator that exposes the abilities of ZIO. And in real ZIO, this is actually not just a function that accepts the success, but you can also fail it as well. So it's a more complicated data type that will allow you to both, it's a more complicated remote that you can blow up your ZIO or you can succeed it at your liking. Okay, but enough metaphors. Let us actually implement it. So let's go here. Okay, and now let's think about what the argument is as well, right? So the argument is a function that takes some arguments as well. So it's going to be something that we actually don't really care about the return result of this. This could be anything. That's meaningless to us. We only care that the person calls this argument with something. So in ZIO, it's going to be a function of something to anything. We really don't care. We're going to use any to specify that we just do not care at all what this is. But it takes an argument. And what is that argument? Well, it's a function from A to, well, also we don't really care, anything. Maybe units, who knows? But let's just use any's in this case. So yeah, and this is, I believe, called a register inside of ZIO. So it's a kind of a scary looking type signature, but if you think about it, it makes perfect sense. We're basically allowing the user inside of some scope that they create, inside of some function, to we're giving them a callback, with which they can, in their function, complete this effect by passing an A into it. So that's what complete is, and this whole thing is everything. So yeah, that can be a little scary at first, but if you think about it as just a function that accepts a remote control to blow up the ZIO, I feel like that maybe helps. Maybe helps. Okay, and that'll get us back a ZIO of A. And how are we going to implement it? We're just going to kick the can down the road and basically pass our register function down along the line. So cool. Let's implement it. This is going to have to take a type parameter of A. This will extend a ZIO of A. And now we can just do sort of the same thing that we've done previously. And maybe it's going to be a little complicated, seeing as it's going to be like really, really hard to implement. What do we do? All these functions are complicated. Okay, well, we have a callback, and usually we've been calling the callback with an A. So we can ask ourselves, okay, how do we get ourselves an A? Well, there's an A in the register. Okay, well, can I call the register? Well, I can, but how do I call the register? Oh, I have to give it a function from A to any. Do I have one of those? Well, yes. In fact, that's what the callback is. So this is actually different than all the other ones where we called our callback with the value. But this actually, the implementation does reveal what I was just sort of saying, which is that we're inverting the control a little bit. We're giving the outside world the opportunity to continue here. And we're giving them control. We're literally giving them sort of the main thing that we've been using to control the execution of a program to this function. So it's actually incredibly trivial of an implementation because really all the complexity is happening out here. They're defining how they implement the ZIO. Cool. So that's async. And now if I run this, we should see a second wait after it prints the word beginneth. And then we should see the result after a second. So yeah, let me make that 2 seconds in case that was too fast for anyone. So yeah, there async beginneth, and then result was 10. Miraculous. Does that make sense?
I like the async beginneth. It makes it sound very dramatic.
It is very dramatic. This is very important. This is very important stuff. Okay, cool. So hopefully now async makes sense. It's basically how it works in real ZIO too. And now that we have async, we actually can use it to do some much more complicated things. And this one is slightly more complicated and does require some more thinking. And it has a more complicated example as well to prove, to show off its true complexity and power, which is fork. We can now, we have almost the capabilities that we need to do forking, to run 2 processes that take a while in parallel in a non-blocking manner. So, okay, so let's take a look at first what the example code is. So it's that same async beginneth code. I'll make it 2 seconds. It'll complete with, let's just do scala.random, scala.util.random next int. Okay, so it'll finish with an int from 0 to 999. Okay, and so what we want to do is we want to call our async ZIO twice, and we want to chain this fork operator on it, which will have it execute off to the side in the background and return for us something called a fiber, which is basically just like a handle on that running process, which will expose a method. The fiber will expose a method called join, which will allow us to wait for that process that has been forked off to the side to complete. So usually the way it works is, right, you have some effect, right, a ZIO of an A or a ZIO of an int, and then you sort of wait for it to complete, you get back the int, and then you keep going, and you can use it. In this case, and then you might print line or something, right? You could do something else. Instead, we're going to call .fork. So instead of waiting here, it's just going to continue on immediately to doing whatever we want. In this case, we're calling it again, but then eventually calling print line something. And this has been forked off to the side. So it's going to be waiting down here, or executing down here in the background. Eventually, it will return a value, all good. And if we call on the fiber that we get back, join, it will then actually force this initial fiber to wait for the forked one to complete. And so we can get our int back here. And so it'll bind their lifetimes together once again. So we're going to fork 2 of these long running processes, print line, and then we're going to wait on both of them. So we're not going to return early. We're going to wait for these to complete. And then we can get back the result that was calculated here. This is kind of a low-level asynchronous operator. There are higher level ones. We'll implement one next. That'll sort of be one of our final tasks here. But this is definitely going to be interesting enough, a little juicier. But we're going to use everything that we've already written in order to implement it. Okay, so I hope that makes sense. There is a Q&A question. Let me see if that has to do with this. Okay, so the question is, I'm kind of new to ZIO and Scala. Well, welcome.
Great question.
So I'm trying to understand when a ZIO is evaluated from your implementation of zip and flatmap. ZIO object will be evaluated when we call these methods. Right. So actually, let's trace it. Actually, so let me comment this back out because I think that would be good. Luckily, we can use a debugger on one of these things. So let us call. Let's see where this works. So let me do. I think let's do one that's slightly more complicated. Let's do the zipped one because this does a few things. So let's actually trace it. So before I debug it, let's just trace it manually in our heads. So what do we have here? What is this type? Well, the last thing we did was called flatmap. So what we're going to get back, and maybe we could actually just call print line of our flatmap ZIO here. A cat has exploded something in the background. It's all good. And here's what we have. It's pretty ugly looking, but it is a flat map of a flat map of an effect. And yeah, so why is it a flat map of a flat map of an effect? Well, let's see. Because now everything is basically written in flat map because we have, we've written map in terms of flat map and as in terms of map. So therefore in terms of flat map. So at the top flat map is going to be this one here. And then inside of here, we have a print line, which is being called as on, which is going to then sort of invert it and make another flat map. So this is the as. And then internally, we have print line, which was the effect. That's calling basically this lambda right here is basically just this print line message. And so when we call this, nothing is actually happening yet. We're just constructing this nested series of case classes. We're just building a big abstract syntax tree describing our program. Like we're building this complicated blueprint. It's kind of like a recipe, right? Do this, then do that, then do this other thing. We have not brought it to the kitchen yet. We're not starting the oven. We're not, heating up the frying pan. That would be bad if that stuff started happening just because we're writing down a recipe. That would be like creepy and supernatural and dangerous. Probably we'd burn our house down. And that's kind of what it's like working with futures. Is that you think you're just describing things, but things are actually kicking off while you're doing it because they're evaluated eagerly, and there are these handles on ongoing computations, kind of like what our fiber is actually. But a ZIO is not a handle on an ongoing computation. It's a blueprint or description of one. So we just really get back to this nested case class that is constructed from these sort of core fundamental operators that are nested in this way. Some of these are recursive. Flatmap is, I think, actually the only one that's recursive right now. So we have a flat map of an effect, which is this. And so when we finally do run it by calling the run method which is this run method, we're gonna basically execute whatever the run method was for that type. So it starts with a flat map, right? So we're gonna start by calling run. We passed it in a callback, which is just going to say the result was the result, right? Which is why eventually it's going to say the result was nice here. But for flatmap, what it's going to do is it's actually going to call run on the nested effect here. And then it's passing in a new callback, which is going to take the result of that, call this continuation function on it, which is going to get another ZIO effect, call run on that, and then pass the callback. So it's this kind of complicated thing if you think about it all together, but in isolation, it wasn't so hard. We all implemented this together. It wasn't so bad. But trying to trace through it does get a little more complicated. But basically, only when you call run does it kick off actually executing these things. And then it's going to kind of delegate and sort of now recursively call the inner flat map, which is then going to call run again on the nested ZIO, which at this point is an effect, which is simply going to actually just execute the effect, which is finally going to actually print the line here, and so on and so forth. So that's when the actual work is getting done, just right in here when you call the F of that innermost effect. And then it's going to take the result of that if there was one and then continue along and keep going. So yeah, nothing is happening until we call the actual run method, which in this case, we've created this ZIO app trait and made this main method. And what this allows me to do is click this little run button here. So whenever I click this green run button, then it's basically going to execute this main method, which we'll call run, which will execute our effect using run and then print the result out. So that's kind of how it works. I hope that makes sense. It's definitely a little complicated. Hopefully, we took our time a little bit with this, but it's probably can be worth rewatching. And we're going to be, following up and happy to answer some more questions as well.
Yeah, definitely.
But I hope that helps. Yeah, but also I'll push this code up to GitHub. I would recommend that, if you want to poke around with it or potentially add some debug breakpoints and step through the code line by line and really sort of trace out what's happening. That can be a great way to understand. Just really draw it out with a simple example or two. Okay, so now back to the more complex thing, which is going to be fork. And yes, also apologies for the slight noise in the background. We are moving across the country and therefore selling all of our items in our house. So we have some Craigslist people that are shuffling around. Cool. So back to where we were. We want to fork off these processes and then join them back together. So we're going to start a lot of places. We're going to sort of just do what we've been doing, which is implement some interfaces and then get to the actual implementations, just to sort of sketch things out and bring them into relief eventually. So first thing we need is a method called fork on our ZIO trait. And before even implementing it, what does this need to return? Well, we're using their for comprehension, so we know what needs to return is ZIO. And then what does it return? Well, it returns something that we can call join on. So this is going to be a new type, and it's going to be that type called a fiber. So this is going to have some method called join on it. And what does join return? Well, join returns the type of the initial effect that it was called on. So it'll return the initial result. So this is going to actually have to return a ZIO of that initial type of A. So we're going to need to store that A on the fiber here. Okay, so we can have this return a ZIO of a fiber of A. And now our type signature works. Yeah, nothing's implemented, but this is kind of what we're doing. This is where we want to go. We need to make something that returns a fiber, and then we need to call join in that fiber to get the result back. Right. Okay, so let's think through with this little graph here what needs to happen. Because there are a couple of situations, and that's going to sort of account for what seems like complexity here, which is complexity because we have to handle a couple of situations. So this could be either a long-running task or a short-running task. This could take 37 days to complete, or if you have a really slow network connection, or it could just take, it could just be, it could be something that's ZIO succeed now and return basically immediately. So if it's returned immediately, we need to make sure to sort of hold on to that value such that when you call join, which might, maybe this one takes longer, sort of print line takes longer, you do some sleep in here. It may have already completed by the time we're evaluating .join here. So we need to make sure that we've stored our result and we can basically return this immediately. Also, however, this might be taking a long time, 37 days. And then when we call join here, we need to make sure that we wait right here until that ZIO has finally completed. So there's these two scenarios, the sort of the early completion before anyone who's waiting for it has actually started waiting for it, but someone might wait for it eventually, and sort of, I guess, late completion where someone has already started waiting for it and we want to make sure that they're updated. So how do we handle all of this? Okay, well, it turns out we're going to need to make an implementation of this that's going to sort of be more concrete. I'm going to call it fiber context for now, though we can change this around later. Maybe I'll just call it fiber impl or something. And the reason for this, I could implement stuff here, but because of the covariance that I want here, I'm going to have to be doing some things that are not super covariant, and therefore the compiler would yell at me. So if you don't know what that means, don't worry about it. There's another video we have on variance that should help a little bit. But basically, if we just have this extend fiber of A, we can then do non-covariant things inside of this implementation. But just because this implementation does satisfy the variance annotations, we can have this extended, and it's all happy and good. Okay, so that's one bit of complexity. We have the fiber in place. You can mostly ignore that and pretend this is all one type. So we basically need something that stores the result in case of the early completion, right? If it finished early, we need to hold on to that result such that when more people try to join in us, we can just give them that result immediately. So let's, for now, and Adam can help us make this more concurrency safe in the future, but for now we're going to be super simple, and we're going to have a maybe result, right? Which can be just an option of A. And we can start this out as none, right? Pretty simple. And then to implement our join method, def join, like this, the simple thing would be to simply like, okay, well, maybe a result, we can match on it. And if we have the result, the A, then we could simply call like ZIO.succeed now or something, right? The A. And in the none case, we can, I don't know, explode. There's nothing really we can do. And this is that other situation, right? Where someone has called join. This is the early version where we've succeeded. And here's the late version, which we have not yet succeeded. So we have to figure out what to do in both of these cases. But this is kind of the beginnings of an implementation. However, the other thing we need to do is actually start, like, how are we going to have maybe result be kicked off? Clearly, that also needs to happen here. If we look at this sort of very simple ASCII graph, the second we call fork, we start evaluating that, that effect in its own fiber. So we have to have some kind of method called start, perhaps, which is just going to return unit. And in a side effecting manner, it's going to kick off that effect, which might seem dirty or something or wrong, that we're not supposed to start off ZIOs unsafely. But if you, I mean, at the end of the day, we kind of, that's what we're doing when we call run. And a fiber is sort of our version of the ZIO-ified future, right? It is this handle on an ongoing effect. So we're going to actually need to start it, and it's not really pure anymore. But well, because
and I think the other thing is, if you go to the fork method doesn't return a fiber; it returns a ZIO of a fiber. Mm-hmm. So we are doing this effect when we kind of start the fiber, but then we're putting that in another blueprint that's describing the act of starting the fiber.
Exactly. The fiber itself is not pure necessarily, but we're controlling its construction. This is kind of a pattern known as correct by construction, where basically we're only exposing the interface that allows you to do things in our nice lawful way, such that you're not going to end up in a world where things are bad and sad. And internally to the library, in our private implementations, we can run things and do whatever we want, but we're careful that the API that we expose is exposing things that are going to maintain these invariants and nice laws that we want to preserve.
Yeah, so, and I think it's also reflecting a reality that like these operators of like joining or forking are blueprints, but like the fiber is a running thing. Like the fiber is like 100% not pure. There's like nothing, there's no point in pretending anything around that. Like when the fiber when the fiber is going, like that's like a future. It's like actually going.
Yeah, the functional programmer in me wishes there was some way of implementing this without ever doing anything at all, but that would be very useless. So at some point you have to accept side effects. It's an inevitability of the world. Okay, so let's start with start. One way to do this is to have some kind of, well, we're kind of basically going to delegate to the nice work of the Scala ecosystem and Java and the JVM, and we're going to use an execution context. So let's do execution context dot global. We can make this nicer eventually, but this execution context is going to handle having like multiple threads for us, and we can call this execute method, which accepts a runnable, which guess what's a runnable? One of them is just a function. So a runnable can be described as a function, and it'll submit this to its own internal pool of threads, and it'll handle that for us. So this is actually going to be pretty optimized just out of the box. Not perfect. We can get into sort of more real world concerns and optimizations eventually, but this is not a bad start. What we don't want to do is just call, and without having this, we don't just want to call run on our effect. Speaking of which, we need an effect. So let's get ourselves a ZIO of A in here. There we go. So we don't just want to call ZIO.run in here. That would be sad, because that would just basically not, that would not be very performant. We would just be executing it on the current thread. And if this blocked, then everything would be blocked and we wouldn't really get any parallelism at all. So that's why we're going to use this global execution context to take care of some of that for us. Okay, and now we can get ourselves a callback. What are we going to do? Well, we're going to update our maybe result variable equal to sum of A. When it completes, we are going to update that, which is obviously not concurrency safe, but I think it'll work okay in our situation here. And in the future, we're going to talk about some lower level primitives to making this actually concurrency safe. But that'll be a juicy follow-up episode for those who are interested. But semantically, this is basically what we want to do, minus the fact that there could be some race conditions here. Okay, so now when this completes, we'll have had a handle on it. So that'll handle the early case where we've completed before we've called join. So that would work. But this one actually is going to take 2 seconds, which will probably be longer than it takes to call print line and to fork both of these things. So we need to handle the case where by the time this has been completed, we don't just want to update the maybe result because someone is already waiting for us. So how do we handle that case? Well, we're going to actually have to store one other thing. So this kind of enables, if this is a sum, this is going to be fine for people who call join after we've completed, because we have the result and we can just give it to them right away, which is what we do here. But in this case, we kind of need to do the opposite, which is we need to tell the person waiting on this fiber needs to tell the fiber, hey, call me back when you're done. When you have the results, I will continue. And this is why we need to do 2 things. We need to store some callbacks. We could get away in this case with storing a single callback, but generally multiple people might try to call join in the same fiber. So let's just be very silly and just call a list of callbacks, which is going to be a function from A to any. And I could just do list.empty to start with. And I made this also a var, so not concurrency safe. There could be some problems here, but this will work in this simple case. So this is going to be a list of, that's okay, that's annoying. I'm just going to have that untyped. You get what it is. Okay, so in this case, we're going to add a callback explaining what to do. But how do we get a ZIO back out of a callback? How do we do that? How do we get a ZIO that we can complete with a callback? Well, that's why we implemented async, or one of the reasons we implemented async, right? So this is basically complete is the callback. It's a function from A to any. So we can update callbacks and set this equal to this callback plus the remaining callbacks. Let's add our callback to this list of callbacks. And so this effect that's been waiting, will get completed once ever this callback that we're storing is completed. So we have to actually do 2 things when we get our result back. One of which is store the result for people who have yet to call join. But for those who have already called join, we need to store the result for people who have yet to call it. But for people who have already called it, they have added a callback to this callbacks array, and then we need to iterate for each of these callbacks. Callback, we want to call the callback with the results of A. And that's the implementation of fiber impl. So a little complicated looking, but we needed to handle these 2 cases of early completion and late completion. Those are not technical terms. I just kind of pulled them out of my butt. But I hope that helps explain the sort of the 2 situations that we need to deal with and sort of why there's this complexity. Callbacks for the future and a result for the past. Okie dokie. So now we can actually implement some of these things. And it's going to be much simpler because we've already taken up most of the complexity. So fork is basically, it doesn't take any arguments, right? We're not using anything. Oh, wait, yes, we are. We're using ourselves. So there are no extra arguments except for the ZIO effect that we're forking. So let's create a case class called fork, which is going to take a parameter A. It's going to have a nested ZIO. And this is going to extend a ZIO of A. And then we can implement it. Oh, no. It's going to extend a ZIO of a fiber of A. So it's a little trickier now. My brain is clearly struggling. Okay, let's move this over so we can see. Okay, so we need to call our callback with the fiber of A. No problem. So what do we do? First, let's make a fiber of A. How do we make a fiber of A? Well, we can make ourselves one of these fiber impl things, which is I made a class, so new fiber impl. And we just give it a ZIO. That's what it needs. And then we call start, which will kick it off in the background. And I should probably give it those little curly cues there, parens, to indicate that it is side effecting. And then we can call our callback finally with our new fiber. Great. So that really does encode the semantics that we were describing, which it kicks it off off to the side, yeah, and then exposes this type that allow people to join it back when we're done. Okay, and is there anything else? I think that's everything. I think we actually did it. Why is this sad? Remove redundant parentheses. Okay, no. Let's Let's see. All right, so let's see if this works. I have no idea. It's going to take 2 seconds to complete 2 random numbers. We should basically see async beginneth getting printed twice, potentially, and then print line, nice, getting printed out. So maybe we'll see async beginneth, nice. And then 2 seconds later, we should see 2 beautiful ints printed out to the screen. And the order of nice in those messages might be different depending. Okay, and this is where I mentioned at the very beginning that we might have ourselves a race condition because it exited early, right? So I did warn us of this occurrence. And that's because in our implementation of main here, it's finishing this before we finished everything else. So what we could do, just a hacky thing to do here, would just be to call like thread.sleep, and we know how many seconds it's supposed to take. So let's take 3 seconds and wait for it, so that just the JVM doesn't quit. Oops, and I think it's gonna. Okay, I ran the wrong thing. Where's forked? Here we go. So now we'll see. For real, hopefully, it'll run these things. Nice. So yeah, it worked, and it's running them in parallel. And we have concurrency and parallelism. And as I mentioned, these might have been out of order sometimes, just because fork is actually, it's calling start and is submitting it to that execution context that might just take a hair longer than it does to just flat map and get to the print line. So that's totally fine. And that's great. That's beautiful. And now we can implement, this is, as I mentioned, sort of a lower level combinator. We can implement higher level combinators like zip par, which basically does the same exact thing, except in a simpler way. So how do we implement zip par? So we basically want to run async ZIO twice here. And actually, let me complete it with that random number again. Okay, so let's implement zip par. And it's basically going to take some value. Oops. Oh no, zip par. Oh, it's taking that. It's taking another ZIO effect. It's just like zip, right? Except, actually, let's go down to zip. It's just like zip. So I can even take zip, except it's part. So that won't work. But we want to call fork on each side. Actually, we really just need to call fork on the first one and get a fiber. And then, because we want to wait, we need to wait for both of them. And then we could say f.join. And then we have the result. So hopefully this only takes 2 seconds instead of, 1 second. I'll make it 2 seconds. So hopefully this only takes 2 seconds instead of 4 seconds. Let's see what happens. 1, 2, 3, 4, 5, 6, never finishing. Oh, it exited early again. I thought did I delete the thread sleep? Oh, I did delete the thread sleep. I did not delete the thread sleep. I might have screwed something up here. Let's try 1 second. Why is it not telling me of the result? 1, 2, 3, and then it finishes. Huh, did I screw something up here? Self.fork, I'll fork both. F2, F1, B should be F2. I don't think that matters, but I might have screwed something up. We had such good luck. Okay, now it's working. I guess I might have introduced some kind of race condition by maybe, what did I just have a second ago? Maybe what I did didn't make sense. I was trying to be clever. Is that what I had? No, I had that. And I got A out of f.join. So I was not forking that. Then I was joining the first one. Yeah, I don't really see a problem with that. Do you see anything, Adam, here? Did I?
No, I don't think there's anything wrong with this specifically. I think this may be where we kind of did things in a way where we said like, hey, they may have a concurrency safe, and we may have run into that a little bit. So I think maybe for next time we could definitely put it on the list to spend some time on that.
Yeah, I think that actually definitely might be the case here, because there's a chance that this maybe is none here. And so it's basically, we have a situation where something's never completing. So I think that's definitely the case, because this is not concurrency safe. So that'll be a bonus. At least we can get it to work.
Yep.
The structure of it is technically correct. The only problem is this race condition. So that is kind of the intention of some of our follow-ups, is to make this, to learn about sort of low-level concurrency primitives. on the JVM in order to make stuff like this really safe and not blow up or be non-deterministic, which it currently certainly is. But I'm happy with what we have. I think we can
Definitely.
I hope that was interesting. Please let us know if there's some areas you want us to cover more. We looked at some Scala techniques like call by name parameters, and we very briefly touched on execution context and this sort of declarative sealed trait based encoding. But I'm sure there are things that we overlooked and didn't touch on. So if there was some stuff that seemed alien or confusing to you that I did, please feel free to message in the Discord, or I guess email us. And yeah, we're gonna keep going and make this faster and fancier and add, you know, the error channel, the environment, etc. It should be a fun journey. So yeah. Oh, of course.
Yeah. Thank you for coming. Yeah, I definitely don't think, because we're glad to have you here. And please, if people have questions, either here or offline, you want to do in the Discord. But no, we really appreciate everyone taking their time and joining us for this. And hopefully it's helpful and providing value for you.
Yeah. Thank you, Rachel. Thank you, Long, for your questions.
Yeah.
Awesome. And also Global, apologize if I mispronounced anyone's name. But yeah, thank you, everyone. And see you next Friday. We'll take it off from here.
Yeah. Have a great weekend, everyone.
Everyone, cheers.
Bye.